So in this lecture, we're going to try to understand perfect numbers as best we can, and we're going to try to classify all of the even perfect numbers, basically get a formula for them. And it turns out they're going to be related to something called Mersenne primes, so we're also going to need to try to understand those. So just to remind you, so a number n is called perfect if it's equal to the sum of its proper divisors. The sum of its proper divisors. What do I mean by proper divisors? So all the divisors except for n itself. So here's some examples. The first one is 6, because 6 equals, let's write out all the divisors. So we have 1, we have 2, we have 3, and I don't include 6 itself, but these are all the proper divisors of 6, and you see 6 equals 1 plus 2 plus 3. So 6 is called perfect. The next one is 28. So this one is 1 plus 2 plus, it's not divisible by 3, but we have 4 and 7 and 14, and that should be all the proper divisors. And we add these up, you see that we do get exactly 28. Okay, so in a very previous lecture, we looked at an equivalent definition. So equivalently, n is perfect. We call n perfect. By the way, I should, this might go without saying, but I'm talking about positive numbers here, and positive divisors. If we sum all the divisors, including their negatives, you can imagine this is not going to be very interesting. So I'm always thinking about positive numbers here, so they're natural numbers. So n is perfect if sigma of n, I'll remind you what sigma is. So sigma of n equals 2n. So sigma of n is the sum of all divisors. Okay. So if the sum of the proper divisors equals n, we call it perfect. If the sum of all the divisors equals 2n, you can see this is just n plus n itself. If we include n in this sum also, we're going to get twice our number. So here we get 12, here we get, if we include 28, we'll get 56, which is 2n. So you might say, okay, well, why do we want to think about it this way? Well, it turns out it's this sigma function, where we include all the divisors, is going to have much nicer properties than the function that just takes the sum of the proper divisors. So for example, sigma of n is multiplicative. Let me remind you what that means. So recall, this is a fact that we'll use multiple times today. So sigma of n is called multiplicative. And what that means, so this means that sigma of a product equals, you can calculate it by doing sigma of one part of the product times sigma of the other part of the product, provided that a and b are coprime. So provided that a and b don't have any factors in common. So times there. Okay, and this is multiplicative. If I don't have this GCD condition, then we say, but we still satisfy this, and then we call it completely multiplicative. But sigma is not completely multiplicative, it's just multiplicative. Let me just recall really quick why that is. So the reason is we had a formula in a previous lecture for sigma of n. P1 squared. So let me write up here. So if n has a prime factorization, p1 to the e1, p2 to the e2, etc., up to pk to the ek, then sigma of n is just given by a formula. So we take all the powers of p1 up to, my exponent, e1. Then we take all the powers of p2, and we we're summing up all the powers of p2. And then each of these we're sort of multiplying together with all the with the term coming with the factor coming from the other primes. So p2 to the e2, dot, 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 and then finally we have pk squared to pk to the ek. So it's a product over some function of each prime. Here it's we're taking the sum of all the powers of each prime. And this kind of formula actually just immediately proves that sigma of n is multiplicative. Because if we imagine we had two coprime numbers, a and b, well, those can't share any primes in common. Right? So a would have to maybe entirely have this term. Either a or b would have to entirely have p1 to the e1. And then one of them would have to entirely have this factor, p2 to the e2. And so we see this product here. Well, some of these will be coming from a, some of them will be coming from b. But to calculate sigma of n, a times b, we just multiply them together anyway. So this is always going to work. Because, again, we have a product over some function involving each prime separately. And whenever you have this, you're going to have a multiplicative function. Okay, so what's our goal? So our goal is to just recall, so it's to classify, basically find a formula for all the even perfect numbers at least. Turns out odd perfect numbers going to be a bit trickier. I'll say some words about those at the end. We'll try to classify all the even perfect numbers. These are the first two, so those are both even. And this is a long story, but the way I'm sure this started is people just started looking for patterns. So we have 6, we have 28. The ancient Greeks actually found the next two as well. So 496, and then 8,128, and this continues. Okay. So what do I mean by looking for patterns? Well, we know some things like it goes 6, 8, 6, 8. So maybe that's a pattern. Probably another thing I want to do is break each number down into its prime factorization. Okay. It's just like if you have a chemical substance, you want to know what its atomic formula, what its chemical formula is, because that will give you an idea of the various properties of the substance. So this one is 2 to the 4, 16 times. I can take out a lot of 2's from this one, and then we're left with 31, I think. Okay, and then this one I did ahead of time. It looks like it's 2 to the 6 times 127. Okay. So we are starting to see some patterns already. It looks like there's a power of 2, and there's a prime. These are all primes here that are showing up. 127 is a prime. There's more. So for example, this 31 here, notice that this is 1 less than a power of 2. It's 1 less than 2 to the 5. And you might notice this 127 is 1 less than 128, which is 2 to the 7. So maybe I'll make that more obvious by writing it like this. So I guess that 3 is also 1 less than 4. So this will be 2 to the 2 minus 1, parentheses. That's the 3. Then I have 2 squared times 2 to the 3 minus 1. And then I have 2 to the 4 times 2 to the 5 minus 1. And then 2 to the 6 times 2 to the 7 minus 1. So it looks like this power here is 1 more than the exponent of the 2 in the prime factorization. And if you stare at this, you might see another pattern here, which is, look at these exponents here. These don't look very random to me. It looks like these are all primes. In fact, these are the first 4 primes. So 2, 3, 5, 7, those are the first 4 primes. Well, that's rather interesting. What would you guess the next the next perfect number, if we wanted to create the next one, what would you guess it would be? I can tell you what I would guess. I would guess 2 to the 10 times 2 to the 11 minus 1. Okay, so 11 is the next prime. And it turns out I would be wrong. So this is actually not perfect. Okay, so what's going wrong here? That seemed like a very nice pattern. Well, the problem is, you see how we're always getting a prime here? These are primes. It turns out that this number here is not a prime. It's actually 23 times 89. So essentially, that will give us too many factors. If you calculate the sum of all the proper divisors, it's actually larger than this number itself. This number, by the way, is 2,096,128. This is not perfect. Let's make sure I note that. So not perfect. Okay. So let's just observe something. So it seems here's our pattern. So here's our guess. This kind of number, so we'll call it 2 to the this will be 2 to the k minus 1. So I guess the exponent on the 2 will be k minus 1. So 2 to the k minus 1 times 2 to the k minus 1. Our guess is that this is perfect. But only when 2 to the k minus 1 is prime. Otherwise, it turns out we just get too many divisors. Well, how do we come up with this guess? All we did was sort of try to observe some patterns. Okay. And I should actually mention that it does turn out that this next one, 2 to the 12 times 2 to the 13 minus 1, this one is perfect. And that number ends up being 33,550,336. And this number here is prime, 2 to the 13 minus 1. So that's even more evidence for this kind of condition here. So if 2 to the k minus 1 is prime, our guess is that this is just going to always produce a perfect number. So let's try to prove it. So our goal, in fact, let's be really ambitious here. It turns out if you check all the numbers up to this, or even higher, you don't get any other perfect numbers. They all have this very specific form. 2 to the k minus 1 times 2 to the k minus 1, as long as this 2 to the k minus 1 is a prime. So they all seem to have that form. So we're going to try to prove that n is a perfect number. Let's say an even perfect number. If and only if n equals 2 to the k minus 1 times 2 to the k minus 1, in parentheses, where 2 to the k minus 1 is a prime. Okay. So in other words, all the even perfect numbers look exactly like this. And you can see this statement here actually has two parts. Right? So first of all, there's one part that's a little bit easier than the other one. So the easier direction is this direction. So yeah, there are two parts here. The easier way is assuming I have a number of this form to show that it's a perfect number. So we'll do that first. That's actually due to Euclid. So this is from ancient Greece. They're already able to prove that all numbers that look like this are perfect. Let's actually see that right now, so it's not too difficult. I should say it is a bit difficult, but the difficulty is actually sort of hidden here. So all we're going to use in this proof is the fact that this sigma function has this really nice property of being multiplicative. So let's prove it. So suppose, well, let's say I have a number of this form. So suppose n equals 2 to the k minus 1 times 2 to the k minus 1. This minus 1 is up in the exponent. This one is down here. So let's suppose this, so n equals this with 2 to the k minus 1 prime. So we'll suppose that's prime. Well, then what do we do? So then all I want to do is compute sigma of n. So sigma of n is, well, it's sigma of a product, right? 2 to the k minus 1 times 2 to the k minus 1. And this product suggests that I want to use this multiplicative property, right? Whenever I have a product here. One thing I have to check, though, RD is actually relatively prime. RD is co-prime. I have a power of 2 here. That's only going to have 2's in its factorization, in prime factorization. And I have something here that will not have any 2's in its prime factorization because it's 1 less than a multiple of 2. So these are indeed co-prime. So I'm allowed to do this. I'm going to use the fact that sigma is multiplicative here. So the sum of the divisors, all the divisors of this are sum of the divisors of just the power of 2 times the sum of divisors of this part. And we'll see if we can go further. So what is actually the sum of divisors of this power of 2? Well, I claim it's actually this 2 to the k minus 1. Why is that? Well, it's because the sum of divisors of a power of 2 is just 1 and 2, and then 2 squared, and then 2 cubed, and then all the way up to 2 to the k minus 1. Right? These are all divisors of just this power of 2, because 2 is prime. But this is a geometric series. So this is just given by the formula 2 to the k minus 1 over 2 minus 1, but that's just equal to 1. So this actually just equals that. And then this is going to equal, well, do we know what this is going to equal? Yes, we do, right? Because this is a prime, 2 to the k minus 1. So what are all the divisors of this prime? Well, it's just the prime itself and 1. So the prime itself plus 1, which is going to be 2 to the k. Okay, and we're done because this actually shows that n is perfect. Do you see it? So n is 2 to the k minus 1 times this. I see, and I can write this as 2. I'm going to take out one of these 2's as 2 times the rest of it. So what's the rest of it? 2 to the k minus 1. I took out a 2 times 2 to the k minus 1. And this is just n. So that's equal to 2n. Which means that sigma of n is 2n, so n is perfect. So we're done. And that's that was Euclid's contribution to this proof. So if we have a number of this form, it's an even perfect number. Let's look at the next part. So the next part of this proof is, well, we want to show that, so here's the second part. This actually came much later, and a lot of people worked on this in the intervening time. So this was due to Euler in the 1700s. So this theorem is called the Euclid-Euler theorem. Really, it was this direction due to Euclid, and then this direction due to Euler. So Euler proved that if I have an even perfect number, it must be of this very specific form. Which seems really tough to actually prove. Like how I'm only allowed to use the fact that sigma of n equals 2n. That's all I can leverage. But I need to somehow prove this of this very specific form. Okay. So yeah, it's no surprise that this came much later, this direction. But it turns out it's actually not as hard as you might think. And in fact, I'd actually encourage you to give it a try on your own. See how far you can get in arguing. So all we know is, let me write out maybe the first step. So let's start by let n be an even perfect number. Be an even perfect number. What does that mean? All it means is, well, n is even, and also sigma of n is 2n. My goal is to show this, that n has to look like this. Yeah, I'd encourage you to pause the video, give it a thought. I remember when I first saw this problem, it seemed like a rather fun problem to try. I think I did sort of glance at a proof and saw that it didn't take up much space on the page, so that sort of encouraged me to give it a try. But I remember it still took me several hours to find an argument. It's the type of thing, too, where the Euler's original argument is probably pretty involved. But then over time, people sort of simplified the argument to where it doesn't take up that much space on the page. But I'm going to go ahead and try to work through this argument. So, well, we know this. Let's also leverage the fact that n is even. So, how do we do that? Well, let's write n explicitly as a power of 2. So, n has a prime factorization. We can take out the factor of 2 and we'll just times whatever else. So, let's call that m. And e here is going to be at least 1. Okay, it can't be 0, so we're going to try to use this fact. All right, well, let's take a look at sigma of n. So sigma of n is sigma of 2 to the e times m. And again, I want to use the fact that sigma is multiplicative, and I can because m, we're assuming that has no powers of 2. So m is odd. We take out all the powers of 2. So this is going to be sigma to the 2e times sigma to the m. And just as before, we know what sigma to the 2e is. It's just this geometric series formula again. So sigma to the 2e is going to be it's just going to be 2 to the e plus 1 minus 1 by the geometric series. Sigma of m, we really have no idea. M is odd, but that's really all we know. Okay. Well, we haven't really used this yet, so let's use the fact that sigma of n equals 2n. So since sigma of n is 2n, here's my n right here. So 2n is 2 to the e plus 1 times m. But that has to equal this. 2 to the e plus 1 minus 1 times sigma of m. So 2n. Okay. Well, I kind of want to understand this better. So let's try to solve for the sigma of m. I don't really know what this is. So it's going to be 2 to the e plus 1 over 2 to the e plus 1 minus 1 times m. Okay. So this is rather interesting. One thing to note here is that sigma of m, well, that's the sum of all divisors of m, including m itself. But this number here, like if e is large, this will be something like, a power of 2 over 1 minus that power of 2. So 8 over 7 or 16 over 15 times m, right? So that's going to be a little bit larger than m. But maybe what I want to do here is write this sum in a way that sort of more obviously includes the divisor m itself. So, well, what I can do here is, well, let's do this trick. So let's write the numerator as 2 to the e plus 1 minus 1 plus 1. I'll subtract a 1 and then add it back again. Why do I want to do that? That's so I can sort of split this part off. So 2 to the e plus 1 minus 1 over 2 to the e plus 1 minus 1 m plus, so I'm splitting the numerator apart like this. I have this over to the denominator plus this bit over to the denominator. And we're both going to have an m. So this is going to just be, I guess, m over 2 to the e plus 1 minus 1. And again, why am I doing this? See, I just wrote m in a fancy way here. So it's just 1 times m. So it's just m plus something else. And this is useful because the sigma of m, after all, it's the sum of all divisors of m, which includes m itself. We can see that explicitly here. And then this has to be the sum of all the rest of the divisors. So this is the sum of all other divisors, right? Because it's sigma m equals m plus something. All other divisors of m. Okay. Well, what do we do now? So, how many other divisors does m have? I mean, it at least has 1, right? 1 is always going to be a divisor. I noticed something else interesting here. So this denominator here, I'm doing m divided by something, and somehow this ends up being an integer, right? This is an integer. That means that 2 to the e plus 1 minus 1 is a divisor of m. So this has to divide m. Okay? And also, I should note that this denominator here, 2 to the e plus 1 minus 1, that's not just 1. That's because e is at least 1. Right? So this is at least 3, this denominator here. Okay, so we have some divisor of m here. And now things start to get a little weird, because doesn't that also mean that this whole thing right here, m divided by some divisor of m, that's going to be another divisor of m. So this is a divisor of m. This whole thing right here is a divisor of m. Our whole thing divides m as well. Okay? But this seems impossible. So the reason this seems impossible, it's almost impossible, it seems impossible because sigma of m is the sum of all the divisors, and I see m here, and I see some divisor of m here, but I don't have any more space in the sum for 1, for example, right? 1 is a divisor of m. But I see m, I see another divisor, which is going to be one part of this sum. But somehow that's also equal to the sum of all the other divisors of m. So we don't quite get a contradiction, but we immediately get that this thing right here has to just be the number 1. So we get that m over 2 to the e plus 1 minus 1 just has to be the number 1. Because if it's not, then we don't have enough space in this sum for all the divisors, and sigma m is all the divisors. Right? What does that mean if this is 1? It means that m, we actually know exactly what the form of it is. It's 2 to the e plus 1 minus 1. It's 2 to the e plus 1 minus 1. So n is 2 to the e times 2 to the e plus 1 minus 1. And furthermore, this has to be a prime. Why is it a prime? Well, there are several reasons, but the clearest to see is sigma of m is m plus 1. Right? So m only has 2 divisors, m and 1. Doesn't have any space for any others. So the only numbers with exactly 2 divisors are primes. So this must be a prime, and n has this form. So we essentially proved this reverse direction, which was a little bit more delicate. But we proved that if n is an even perfect number, n has this form. Let's make it a little more obvious. So what is e actually? So e is k minus 1. So if we just set e to be k minus 1. Doesn't matter, it's the same form, right? But then this would become 2 to the k minus 1. So n has this form. Okay. So that is the conclusion of something called a prime number theorem. It's not a prime number theorem, a perfect number theorem. It's called the perfect number theorem, also known as the Euclid-Euler theorem. Euclid-Euler. Note that the EU is pronounced differently in both names. So it's the Euclid-Euler theorem. Okay, well, what does Mersenne prime? What do Mersenne primes have to do with all of this? So, we have 2 lingering questions here. So, first, the second question would be, what about odd perfect numbers? Right? We said even here, right? And we really leveraged that fact that this was even, n was even, right? Because we use the fact this denominator is greater than 1. If it's equal to 1. We just got sigma of m equals m plus m. Sigma of m equals 2m. That's where we started, right? So we don't find anything new. But first, yeah, let's let's consider, like, when is this 2 to the k minus 1 actually a prime? We only get a perfect number from this formula if 2 to the k minus 1 is prime. Okay. Well, the first observation is that in order for this to be prime, we need k to be prime. We need the exponent to be prime. Why is that? Well, so if k is composite, so if k is not prime, then k is a times b, neither of those are equal to 1, and so yeah, a and b are strictly greater than 1. Here's the problem. So 2 to the k minus 1 is 2 to the ab minus 1. But I can use the property of exponents to write it as 2 to the a to the b minus 1. And now we're sort of seeing that, well, let me write this out over here. So in general, if you have a polynomial like x to the n minus 1, that's going to factor. Okay, x squared minus 1 is x minus 1 times x plus 1. But in general, this is always going to have a factor of x minus 1. Then it'll have another factor which looks like this. This is actually, if you recall, this is where this would be n minus 1. And minus 2. This is where we got the formula for the geometric series from. So 1 plus 1. Okay, so x to the n minus 1 has the following factorization. So in this case, I'm going to treat this 2 to the a as x. And I'm just going to write this out. So this is going to have a factorization 2 to the a minus 1. Okay, this term here. Times something else. I don't really care exactly what this one is. So, yeah, 2 to the a to the b minus 1 plus, etc. This is going to be a large number. So 2 to the a plus 1. And the point is, this shows that this is not prime, right? Because this is greater than 1, and same with this one. It is greater than 1 because a is greater than 1. So if k is not prime, we can factor it into 2 smaller numbers in this way. So k has to be prime. So k has to be some prime. But that does not actually guarantee that this number is going to be prime. So we can say this is let's say this a necessary condition, just to introduce some terminology you might have seen before. But so it's a necessary condition, but not sufficient. It's a necessary but not sufficient condition for 2 to the k minus 1 to be a prime. Basically, mathematicians have just a lot of ways of saying if and only if. And this is sort of one of them. So what are we saying? We're saying that what would be the corresponding if and only if? So this is prime. We want to say this is prime if and only if k is prime, but that's not true. That's not true because, so you could have k be prime, but this is not prime. So this direction actually is not true. And here's an example, right? 11 is prime. It's the one we saw before. But 2 to the 11 minus 1 is not prime. But in order for this to be prime, a necessary condition is that this has to be prime. So if this is prime, we just that necessitates k being prime. So in other words, yeah, we have this implication. Okay, well, when are exactly these prime? So when is 2 to the k minus 1 prime? So 2 to the k minus 1 is prime for following values of k. I'm actually not going to write them out because there are a lot, but I'll start. So 2, 3, 5, 7. It's all the ones we saw before. So 2, 3, 5, 7, not 11, but then 13 does work actually. So 13, 17 does work, 19 does work. So maybe you think 11 is the odd one out, but now it seems like everything's working. But then we have to go all the way up to 31, and then 61, and then 89. So these are the values of k that make 2 to the k minus 1 prime. 107, 127, 521, 607, etc. There's some big jumps here, and these numbers are getting really huge, by the way, right? Like this number, these numbers are starting to be over 100 digits long. And so one question is, how many of these are there? How many of these are there? So when 2 to the k minus 1 is prime, we call this a Mersenne prime. It's the name we give to numbers of this form that are prime. And it turns out nobody knows. No one knows if this is an infinite. So no one knows. No one knows if this is an infinite sequence or a finite sequence. Maybe there's a largest prime of this form and then there aren't any more. Currently, so the current largest, and this was found in, so this is found December 2018, is this number, 2 to the 82,589,990, sorry, not 993, 933. And this has about 25 million digits. So you might be asking, like, how do you even check something that huge as prime? And normally there's no way to do it. But it turns out for primes of this specific form, or for numbers of this specific form, there are different methods that are faster to check whether numbers of this form are primes, or sort of methods designed specifically for numbers like this. Oh yeah, and by the way, so this is the sorry, it's this number minus 1, of course. This power of 2 alone is not prime. But this is the largest prime. It's actually the largest prime period that's currently known. We know there are infinitely many primes due to Euclid. We don't know if there are infinitely many Mersenne primes. This is also the this is the 51st, I believe. It's the 51st one that's found. 51st found in Mersenne prime. Sorry, I'm running out of space here. Okay, so just to reiterate, we've proven that any perfect number must be, any even perfect number must be of exactly this form here, where 2 to the k minus 1 is a prime. Okay, so, and we call those Mersenne primes. We currently only have 51 of those, but every time we discover a new Mersenne prime, we discover a new perfect number as well. So we also know of exactly 51 perfect numbers. Every time we get a perfect a Mersenne prime, we can use this formula to get a new perfect number. Okay, well, there's one question left, which is, what about odd perfect numbers? Okay, so I said that there are exactly 51 perfect numbers that exist as of the time of this recording. And they're all even. They're all generated from this formula, where you have a Mersenne prime and then we multiply it by a corresponding power of 2 to get a perfect number. Well, what about odd perfect numbers? Well, the question... nobody really knows. So this is also an unsolved problem. So, unsolved problem. So do odd perfect numbers exist? No one has found one yet, but at the same time, no one's been able to prove that they don't exist. So they very well could exist. And I want to sort of give you some idea of how you might think about this problem if you want to start thinking about odd perfect numbers. So what's the idea? Well, we know that if it's perfect, it satisfies sigma of n equals 2n. Right? And we probably want to make use of the fact that sigma is multiplicative when we have a nice formula for it. So our formula is 1 plus p1 plus p1 squared, etc. p1 to the e1. We have 1 plus p2 plus p2 squared, etc. pk squared, pk to the ek. All right, we have this factorization. In this case, this n is odd. We want to find odd perfect numbers, which means that this number here, 2n, this has exactly one factor of 2. So it's exactly one factor of 2. No more. Which is actually rather interesting because now we see this product over here. That means that essentially means exactly one of these factors is even. Is even. All the rest of them have to be odd. Okay? I'm not talking about factors of n, I'm talking about factors in this product. So one of these is even. And in fact, it's not only is it even, it's how to form 4n plus 2. It only has one power of 2. Because we only have one power of 2 over here. And, well, what does that mean? So what if we just take a prime like 3 and we say 3 is involved? So maybe we have 1 plus 3, or maybe we have 1 plus 3 plus 3 squared, or maybe we have 1 plus 3 plus 3 squared plus 3 cubed. Okay, we're not sure. But you'll notice that we're kind of switching from odd to even. So we're adding in odd numbers every time. All the p's are odd. So if we have a 3 to the 1 power is the largest power, that's going to be even. If we have a 3 to the 2, it's going to be odd. If we have a 3 to the 3, it's going to be, this factor is going to be even. Okay. So if one of these factors is even, the exponent has to be odd for that factor. Right? Because of this pattern. If the exponent is odd, we get this to be even. So So we can say exactly one exponent, one of the EIs, is odd, but the rest are even. Okay, the rest are even because we need every other factor to be odd, and we can only get an odd factor if we have an even exponent. So that will actually give us an odd number of odd terms here. Sorry, it's a bit confusing. Yeah, this is sort of maybe the first observation we can make. In the prime factorization of n is going to always look like this: p1 to the e1, p2 to the e2. All the p's are odd. pk to the ek. We know all the exponents are even except for 1, and 1 has to be odd. Okay. And you can kind of keep going, so you can suppose 3 is the one that has the odd power, the odd exponent. So suppose 3 has an odd exponent. Okay. All right, so factor corresponding to 3 is going to look something like this. Let's call it E. And this is going to be, by our geometric series formula, 3 to the E plus 1 minus 1 over 3 minus 1, which is 2. Okay. But if E is odd, right, so if this is odd, then this is even. So this is even. So it's of the form 2k. So we have 3 to the 2k minus 1 over 2, which is just 9 to the k minus 1 over 2. Okay. But we run into problems here. The reason we run into problems is this 9, essentially any power of 9, if you subtract 1, you're going to get something that has a lot of factors of 2. You're going to get something that's actually a multiple of 8. That's because 9 itself is of the form 8n plus 1. If I multiply together any numbers of the form 8n plus 1, I'm also going to get something of the form 8n plus 1. And if I subtract that 1, I'm going to get a multiple of 8, actually. If I divide by 2, this is going to be a multiple of 4. So at the end of the day, yeah, this is going to be a multiple of 4. So this is a multiple of 4. And, that's a contradiction, because if we had a multiple of 4 here, we only have 1, 2 on this side, right? We don't have, that's it. There's exactly one factor of 2. So there's some contradiction here. Contradiction. So what's the takeaway? So 3 has to have an even exponent. So 3 has an even exponent. If there was an odd perfect number and 3 was a factor at all, right? Could have a 0 exponent. But then you can kind of keep going. I'll stop soon. It's just kind of fun to think about this. So say 3 is, say 3 occurs with exponent 2. So 3 has an exponent of 2. Meaning n is 3 squared times a bunch of other primes. Okay, what does that mean? It means sigma of n, which is equal to 2n, by the way, but sigma of n is going to have 1 plus a 3 squared, and then there'll be more stuff. But in this right here, what is that? That's number 13. And so this number here, 2n, it has a factor of 13. Which means that we now, once we decide this, we have now forced n to have a factor of 13. So n is now 3 squared times 13 to some power times more stuff. But then you see what happens is we now need a term here for 13, and then that might even produce more factors. And so, but this is exactly the game that you can play with these kind of we have sigma of n equals 2n, and essentially this is what people do nowadays to search for large, odd, perfect numbers. You sort of go down this tree of possibilities. And every time you make a decision here, that also makes a decision for n, because we have 2n equaling this product. And then that creates another term here, and then that might add more things to n, and you have to sort of perfectly balance both of these sides. So very fun problem to think about, but I wouldn't spend a whole lot of time on it if I were you, because people have been thinking about this for 2,000 years, and still nobody has any idea if these numbers exist. We certainly have proved, probably hundreds, if not thousands, of conditions on odd perfect numbers if they do exist, but nobody has any idea currently. Thanks for watching.